In Haskell, functions technically always have exactly one argument. If we want to model functions that have more than one argument, then we typically use currying. If we want to model functions that have a flexible number of arguments, then we typically would use a list. In some other languages, it is also common for functions to allow having a variable number of arguments. And so like positional arguments, not in a list. And in this episode, we want to look at how we can, if we want to, use Haskell's class system to encode or simulate the same thing. And we're going to discuss a few examples where we might want to use such an approach.
Yeah, welcome to the Haskell Unfolder, a YouTube series where we discuss all things Haskell. As always, the show is live streamed. We invite you to submit questions or comments in the chat, and we will try to show them on screen and discuss them.
Yes. Okay, so let's look at a simple example first. Like we want to define a sum function, but not like the typical sum function in Haskell that takes a list of integers and produces a sum, but we want something that looks a little bit like I've written down here in the comments, where we have a sum function where we can just add a number of arguments and get the results as one would expect. And we're going to try to get there. By the way, I mean, so this, like when I was still in academia many years ago, like teaching at Utrecht University, I sometimes post this as a task in my Haskell courses to students, as like an exercise task for type classes, because I think it's a good exercise. It's neither completely simple nor is it extremely difficult, but we can just see where we get. So if we take a naive approach and we want to just define some kind of class that models this, because I mean using a type class is reasonable, right? Because like sum, if you look at the type of sum in this first example, it would have something like int to int to int to int, right? For example, and in the second example, it has type int to int to int to int to int. So we need to use to be able to use sum at different types, and there is also different behavior, namely like a different number of arguments we want to sum. So like using the overloading mechanism seems adequate. So if we like the first approach we might want to try is to simply say, okay, let's assume we have a method of the sum class that is also called sum. And it just has type A. That is something that we could be trying. And then we're going to define an instance of the sum class for integers. And that is basically the zero argument case, right? If we have no integers to add at all. And in this case, we would have to produce 0 as the result, right?
Because so the int here is the result. Right, we have no arguments, then we have only one result, which is the int.
Exactly, yeah. And then we need another case, and because we, of course, I mean, I could now also go and like define an instance for int, arrow int, and so on, and that would actually work, right? I mean, I could do something like that, but that is getting boring rather quickly, and is only going to work for a for a fixed number of different cases, right? So what we want is some. Yeah, sure. I mean, if you're happy with that, but I mean, what we would like is some sort of inductive way of defining this, right? We would like to be able to say, okay, so if we already have an instance of sum for A, then we can also add one more argument, right? That is. That's kind of what we would like.
Yeah.
But here we are immediately running into a problem with the implementation, right? Because we're now getting an integer argument, and then we have to produce something of type A, and we would like to use the sum function at type A. I'm using a type application here to emphasize that. And then if we want to somehow modify this, we have to write here something which is going from type A to A, right? That's the type of the whole for an unknown type A. We don't know anything more about the A type except that it is also a member of the sum class. But so this is essentially parametricity, right? We did an episode on parametricity. If we have no further operations, there's nothing here we can do except basically just reuse the result. And now we have achieved the goal of writing a function that takes a flexible number of arguments, but it will always return 0. So it's not a particularly useful function. Now, you might wonder if we could write something like sum at the type A plus I, right? If we could assume more things about more operations on A. But again, if you kind of look at what is the shape of these types A that we are considering here, so A could be integer, A could be integer to integer, A could be integer to integer to integer, and so forth, right? And in general, these are function types, again, of variable-arity. And like apart from the sum class that we are just defining them to be a member of, it's not really reasonable to assume that we have addition on those, right? So really, this is not the right approach. The better approach is that we want to pass extra information about this I to the recursive call, right? To the recursive call. And that means that it would be better if this sum function that we are recursively calling here has an input that we know about. And so the next step, or the next approach that we could try to use is, let's say we are not actually defining the sum function we eventually want to define, but we're going to define an auxiliary function which we give an extra integer argument to, which we can look at as being the accumulated sum, right? And then in the case where we have no arguments or no more arguments, we are now getting an accumulated sum and we're simply returning it. And in the case that we previously failed to define, the sort of like the inductive step, we're getting an accumulator, which we probably should make strict, and we are getting an extra integer. That is because we now have something of type int to a to define, and we want to make a recursive call to sum prime now at type a, and we have to pass it an accumulator, which is updated. Namely, we are going to pass it the accumulator plus I. And actually, now I don't even need this type argument anymore because it will be correctly inferred. Okay, so this type checks. And of course, it's not actually the function that I wanted to write because it now always takes an integer. So I could no longer use it with 0 arguments, right? So the extreme case here would also be to say sum without any arguments should be 0. That is something that we now could no longer write, but we can recover that function easily by simply calling sum prime with an initial accumulated sum of 0. Okay, so that is a definition that seems okay, but the question is, can we actually use it? Like, does it work in practice? So we can try that out. And if I try to call sum of 1, 2, 3, and I try to let HLS evaluate this, I'm getting a strange type error. Now, the type error is perhaps, like from the message, not very easy to understand, but if you think about it, it is not so strange that we are getting a type error, because if we now have an expression such as this, it is no longer clear whether this is a partially applied function, right? Whether we still want to add more arguments to it, or whether this is actually finished, like a finished call, like we are expecting an integer. And so basically, GHC does not really know whether, at what type we want to look at this, right? And so it does make sense to provide some contextual type information and say that we actually want to look at the entire expression as something of type int. Okay, and if we make that type annotation and try again, then we're getting a different type error.
Making progress.
Some
It's a simple
progress.
type error.
Yeah, it's still not really done. Now, this is a weird interaction between the way that the class system works and the fact that number literals are overloaded, and the fact that there is some amount of what is called defaulting going on, right? But the first observation is that if we ask for the type of 1 in Haskell, then the type of 1 is a type A that is in the num class, right? So if we simply look at the type of something like, let's perhaps not write that down explicitly, but if you simply look at this expression here, sum applied to 1, 2, 3, all that GHC sees about the arguments here is that they belong to the num class. So it is looking for an instance of sum for a function type, but the argument type is not known to be int, right? The only thing that it knows is that we have an argument that belongs to the num class. And the way that instance search in Haskell works is it does not really take the available instances into account, right? It tries to match with this instance int arrow A, but it can only match if it already knows that the argument of the function is an int. And at this point, we don't know that, right? And then at some point, defaulting kicks in, and defaulting turns it actually into type integer, and that's why we get this particular error message. So one way to fix this, but not a very satisfactory way to fix it, is to annotate the arguments as well to be ints explicitly, right? And then it actually works. But this is not very nice. Yeah.
Before we move to a slightly nicer solution to this, there's one sort of semi-serious comment, which I thought I might actually bring up.
Yeah, sure.
So this, Pavel says, oh ho, runtime type polymorphism, blasphemy. And I thought it's kind of interesting because this is not runtime type polymorphism, right? We are figuring out at compile time what instance of sum we need. And so this is completely static, right? At runtime, we're not doing any kind of dispatch. So I thought that was like an interesting sort of side remark to just to think about. It's not, so this is different to what you would have like a overloading in C++ or something like this.
Yeah, the whole class resolution is happening at compile time. Yeah.
Right.
And these are still static type errors that we're getting. Yeah. So the slightly better way to fix this, and this is also part of the reason why I'm showing this, is because I believe this is an independent technique independently of the whole variable arguments. Even if you're never ever using variable argument functions, this is an independent concept that is interesting to know, which can often help improve sort of the type inference behavior of overloaded functions. Is what we can do here is we can replace the instance for int arrow A with an instance for b arrow A. The goal being that it now matches independently of what the argument type of the function is. So even if GHC does not know yet that we have an integer argument, right? Just simply by knowing that we have a function, it can match this instance. But then in the preconditions of the instance, we can add a constraint, an equality constraint that says b has to be equal to type int. And this almost looks like an identity transformation, but it really changes the behavior of the instance, right? Because in the previous form, we are saying this instance can only match if we already know that the function argument is an int. And now we say this instance matches at the moment that we know that we have a function, but then we require the function argument to be int, and that can then be used in type inference. And so if we write the instance like this, then we can actually get rid of the annotations on the arguments again, and it still works. And I can also add a few more and show that it changes the result. Okay? So this is this is the basic idea, right? This is in the simplest scenario, simplest function, the basic idea of doing this. Now, in the rest of the episode, we're going to look at small variations of this theme. Okay, so so another thing we might want to do is to say, like, okay, perhaps we do not always want to sum things up. Perhaps we want to do other things with our arguments. And a relatively flexible thing we could be doing, or a goal we could be having, is to simply collect the arguments in a list, say, right? Because if we can collect them in a list, then we have still all options, right? We could sum them or reorder them or do whatever we want with them. If we can write something that collects the arguments in a list, then we can plausibly do anything, right? So let's see if we can do this according to the same principle. So let's write a class collect a, and again, like for initially at least, let's consider that we only want to collect integers, right? So we're going to talk about this a little bit more afterwards, but as a first step, let's assume that we're going to collect integers. So again, I'm just basically going to have this accumulated list of integers here as an argument, and then produce an a. And then I have a case, like a base case, where I say I want to have the final list of integers. So there I'm getting this accumulated list and I'm spitting it out. And then we have an instance which I'm going to write very similarly to the one before. Not some collect the arrow a, or collect prime of the list xs, and now an additional integer x, I mean, I could also call it I, is a recursive call of collect prime where we simply cons x to this list. And then again, we write a wrapper function, which is of type collect a double arrow a. And here we, this time, initialize our accumulated list to the empty list. And now we can try whether that works. So we can say collect 1, 2, 3, and we want to look at it as a list of integers. And it does work, but we do get the arguments in the reverse order, which kind of does make sense, right? Because we if you look at it, sort of like we have an integer argument sort of at the very end. Like if you look at this call, it's kind of right at the outside. The outermost call is the one with the 3, and then we take that argument and pass it in sort of as the first argument of the accumulator. Right, and so it becomes the first argument of the resulting list. Or is that right? Am I confusing myself?
No,
I guess I should. I guess I should argue the other way around. So, like, I mean, if we look at the base case, collect itself is initializing to the empty list, and then and then we go from the inside out. Yeah, that is better. And then we first process collect 1, and then so we insert it at the front of the accumulator, and then we pick up the 2, and we insert it at the front, and then we pick up the 3, and we insert it at the front. Sorry, yeah, that explanation is better. The first one was weird. And so we get out the accumulated list in reverse order. But this is not a big problem. I mean, one like if we wanted it in the original order, one thing we could do is we could just add a reverse here, right? And then if we do the whole thing again, we get everything in the order we expect. And there are other tricks one could play as well. Like one could switch to some sort of continuation style here, where we have a list of int to list of int argument, or difference list, if that rings a bell for some people. But I'm not going to explain that variant. Point is, you can do all these things if you want to. Now, you can ask yourself, why would you want any of this? Right, and so to some extent, it is essentially just sort of an exercise, I guess. Like to some extent, you can argue that this is just a cute trick, But there are still a number of scenarios in which this can be useful, right? So one is like if you just simply want to model within Haskell as some sort of embedded DSL, another language that has this feature, and you want to be syntactically close to it. That is one possible reason. But another possible reason is that you can be slightly more flexible with this kind of collection functions or this kind of processing functions with variable arguments than you can be with standard list syntax, because you can do things that are more heterogeneous as well, right? So in the example that we have been looking at so far, we have always been processing things that are all of the same type. But we can also do the same thing with things that are of potentially different types. And while Haskell has a notion of overloaded list syntax, it is nevertheless not possible right now to use this overloaded list syntax that looks like with the square brackets and the commas, to use that for heterogeneous lists. So the moment you want to define heterogeneous lists, you have to define your own data types, and then you have data types that have constructors that have names, and then syntactically that sort of stuff becomes much more noisy, right? So you can say that certainly in a situation where we start doing things heterogeneously, sort of the syntactic the overhead, the syntactic overhead becomes much smaller. So let's look at an example that goes in that direction. So let's perhaps try to define a function that takes a number of showable arguments and essentially just all like turns them into strings and concatenates them. So I'm going to call that, let's say, var show, variable show. And again, we're going to follow the same principle. And here I'm going to use a list of strings as an accumulator internally. And the base case is that we want a single string as an output. And in the base case, we're going to do something like we have this accumulated list of strings, and they're all going to be in the wrong order. So we can do something like reverse this list of strings, and then we can concatenate them, or we can insert commas in between, make it sort of slightly look nicer. Oh, this is not in the prelude. I have to import it. And then our recursive case is going to be similar to what we had before, only that now we are not going to say that we only need a var show A instance, and we don't like put any equality constraints on the B's, but we simply say that we expect B to be in the show class. And in all these cases, we can process this extra argument. And here we are making a recursive call again to the var show on A instance. And we're going to add X to our accumulator, but we're like have to turn it into a string, so we call show X. Right. And now we can again wrap this up in another function and initialize our accumulator to the empty list and try it out. And so now we can do something like false, let's say a character perhaps, and perhaps a number. And so again, I need to annotate the result type. The result type needs to be annotated, but we get a nice result.
So there's another comment from Pavel, which I think I could bring up, and he's reminded of printf here.
Yeah, actually, that's something I wanted to mention, and that is like one of the examples where this pattern shows up in the wild. Let me actually see if I have it open here already. Let's close these. So if you look at the text printf function, which is in the base library, actually, it is it follows essentially this pattern that I've just described. It is a variant of this. So it has an extra string argument, which is a format string, and there is actually a little bit of type unsafety in this particular implementation of printf, because if you come from sort of like the C world where printf I think originated, then the idea is that this format string here dictates exactly how many arguments you want and of which types they should be. And there are sort of more type-safe and cleverer ways of encoding something like this more precisely in Haskell. But this is sort of a pragmatic effort, and the idea of this one is essentially that, yeah, it doesn't really check whether your arguments are adhering to the format string. You may get runtime errors with this one, but the principle in which the arguments are collected and processed is exactly following the same idea that we have just seen. So perhaps it rather than looking at the actual code, or well, I mean, we can also look at the actual code, perhaps. Let's see. So we see here that printf is also defined as a wrapper around a function that is called SPR. And there is an accumulator that is initialized to the empty list. And SPR is a function that is defined in a type class, like we have seen. And it uses this list of uprintf things as an accumulator. And the string is the format string, which is carried around. And then if we look at the instances for printf type, then there is a base case here, which is basically the base case for strings, right? So that like it is slightly more general, but you can think of this as sort of the base case for strings. And again, we have a reverse in here because the arguments are accumulated in the wrong order and then they're processed in some way. And then we have a case for functions where we're picking up our argument and then we're adding it, in some way to the accumulator, right? So yeah, so this is really a good question, good remark. The same pattern that we have just seen. Mm-hmm. So as a final example, I want to show sort of like a slightly more generalized version of this var show again, where we also we try to collect the things in an actual heterogeneous list, right? To show that this is also possible, and then you can perhaps imagine that you have even more flexibility. So for that we need a heterogeneous list data type. So let me try to copy that in. So this is a list that is like a GADT that is indexed by a type level list. We either have the empty heterogeneous list, then it's indexed by the empty type level list. So I need to enable data kinds for this to check. Or we have a cons, which takes a thing of an arbitrary type and a heterogeneous list, which contains some other types, and then tracks on the type level which types are contained in this. And then we want a show instance for this so that we can actually try it out later. So let me copy that in as well. So I think we had an episode on computing constraints in the unfolder as well, which shows a more elegant way of doing this. But here, sort of as a very straightforward way of doing this, we can simply use standalone deriving to derive a show instance for the empty list, and then following the cons case, we can say if we have a show instance for X and if we have a show instance for the tail, then we can also show this. And I should actually enable the GADT's language extension as well, so that all this is going through properly. And then we can define some hcollect class, which is a sort of version of collect, but it accumulates a heterogeneous list. And here I'm going to get a little bit of extra trouble because I have this hlist XS, which I want to accumulate to A. And so where is this XS coming from? It cannot be universally quantified because depending on how many things I'm picking up, I need to know this. But funnily enough, the result type, sort of the type that we're using hcollect at in the end, is always going to determine exactly which elements we want to have in our list. And so this is a perfect use case for a functional dependency. So we can simply add XS as an extra class parameter and say that A is always going to uniquely determine XS. And this is another class language extension that I'll have to enable. And then the definition is essentially following more or less the same principle that we have before. So let's see the base case, or the base case is that we actually want the H-list out. So, right, and here the XS has to match this XS. And here again, we are getting our accumulated list and we just produce it. And this will again be in reverse order. I'm going to say one word about this at the end, but and then the other case is that if we already have an hcollect instance for XS for some type A, then we can also give an hcollect instance for XS. Sorry, now I have to watch out. So in one way, I have to here. I think I have to. Say if we have an hcollect instance for xcons XS of type A, then we can get an hcollect instance for XS of type X2A, where hcollect of XS and X is hcollect prime, the recursive call where we hcons the X to our XS list. And now, okay, there is another complaint by GHC that it cannot easily see that this instance terminates because we're making one of the class arguments smaller and the other argument larger. But we can see that it terminates, so it's perfectly fine to enable undecidable instances in this case, and there is no problem with that. And then again, we define a wrapper around this, hcollect empty list A arrow A, and initialize this thing to the empty heterogeneous list. And then we can try it out on a similar example as the one that I've been showing above, where now I annoyingly have to specify the types, and I have to specify them in the reverse order, which like it does make it work, but it is certainly not satisfactory again. But actually, this is too much information that we're providing now. All that we really contextually need is that we need to know that we are in a situation where we are expecting an H-list. So we can like sort of use a specialized identity function that says we are operating on an H-list to provide sufficient contextual information here to say that we are not intending to provide any more arguments to this, right? Because then we already have enough information again to match the base case in our instance chain and get the right result. So yeah, so that is the final argument that I wanted to show, and I think. Yeah, I mean, so one remark that is perhaps still in order is that in the previous episode, Etzko talked about going from Java to Haskell.
Oh yeah, I can actually show this if you like.
If you have it available, yeah. So
actually it's interesting because Mikolai earlier commented that this sort of H-list, collecting H-list can only be used if you know the exact type. And it's kind of what you showed as well, right? Where you have to have the full type annotation. Now, you also showed that this is not always necessary, right? And in this case, it actually is fine. Just as long as we know that it is a H-list, we're actually fine. The other comment I wanted to make, and this goes back to your comment that you just made, is that actually there are also cases where the full type is very much visible from the context. So yeah, you mentioned this gRPC example where like some sort of server, and this is an example that we saw last week. And this is an example of a heterogeneous list, right? So this is a weird list where everything of these methods, which are methods of the server, have a different type, right? This is a GDT, similar to the GDT that you showed. And indeed, in this case, the signature fully determines, right, what the type of every method here is. Right? We know we have a type level description of the server, and so we can say precisely we want the methods for every method that the server provides. And in this case, we can do exactly what Andres showed. We can define I've called it simple methods here, which is a var-arc function like Andres showed, where you just have all the methods as a single argument. And so yeah, Andres talked about that. This is syntactic overhead, right? You need to have the construction of the GDT, you need to apply it to something, and then you say this is finally done, right? So the syntactic overhead over heterogeneous list is somewhat ugly. And in some cases, you might prefer to have a var-arc argument. So yeah.
Yeah, it's still a matter of taste, right?
Sure.
But it is it's like, for one thing, it's a pattern that you may sometimes see somewhere, and so you may recognize it and have an easier time understanding it. And also, if you're designing something yourself, you can make a choice, right? I'm not necessarily having a strong opinion myself on what is better, but even here, as Etzko has just shown, this is replaceable, right? You can even offer both options, like and let the user choose which way they prefer. Yeah. Okay. Do we have more questions?
No.
All right. Then let's go.
All right. Well, thanks everyone for watching this episode of the Haskell Unfolder. We'll leave the chat open for a few more minutes. So if you have any more questions, feel free to leave them in the chat, and we'll try to answer them. If not, feel free to leave them in the comments below the video after the episode, and we're always happy to answer questions, criticize other solutions, things like this. So by all means.
Yeah.
So anyway, if you enjoyed it, please like and subscribe, and hope to see you all in
a couple of weeks. I think we're going to have at least a 3-week gap now that we because of Zurich and other things.
Right.
Yeah. Thank you very much. Bye. Oops.